Let's now work through some problems from Chapter 10. So this is the predict the product type question that we looked at with Chapter 9, and we have to identify the functional group we're starting with, and then think about the conditions that it's being subjected to. So first we have an alkene, obviously, right? And in the first step, we are treating it with water and sulfuric acid. So this is a Markovnikov hydration, where the hydroxyl group will be on the more substituted side. So we're going to end up having this as the product. There is a stereocenter here, and so technically we have both R and S configurations. In the second step, we're now treating this with H2SO4 and heat, and that's to dehydrate. Now it seems a little silly, why would you hydrate then dehydrate? But if you think about it, when you dehydrate this, so there's two possible beta positions, but one of those is going to be preferred over the other. And hopefully you remember Zaitsev's rule, and you would know that the major product that's going to develop is going to be this trans disubstituted alkene. It's not going to be as favorable to dehydrate from this side. So you're going to get this as the major product. And so what this two-step process has accomplished is it has moved the double bond from here to here. And this is a very common sequence that you're going to see used during this course. Okay, again, let's look at the functional group we're starting with, which is an alkene, right? And now we are subjecting it to Br2. So that's going to be a bromination. And so we have Br and Br. There is some stereochemistry here, but I'm not always going to worry about the stereochemistry if I see that there's a second step coming up, because sometimes it won't be a chiral center by the end of the process, so it won't matter. If this were my final product, I would need to be sure to talk about the stereochemistry. But in the second step, we're treating it with two equivalents of sodium amide, and we saw that that was a way to make a triple bond. And so we're actually getting the triple bond here, so that's these two carbons, and then off of each of those carbons we have an ethyl group, and so I'm going to write CH2CH3 and CH2CH3. Here's another alkene, and this time we are treating it with HBr in the first step. Recall that this is going to follow Markovnikov's rule, and so we're going to get Br here. We're going to make note of the stereochemistry, but not worry so much about it just yet. Let's see if it's going to matter. The second step is NaCN and DMF. That is an SN2 substitution. So we probably do need to worry about the stereochemistry. So let's draw what the product outcome would have been after the first step. Okay. And then let's think about what that's going to look like in the second step. We know SN2 gives inversion, and so we're going to end up with this product and this product. And another alkene. We're going to do the hydroboration oxidation, which is an anti-Markovnikov hydration. So you end up with a hydroxyl group on the end. And then we're treating that alcohol product with SOCl2 and pyridine, and that's just a chlorination step. So we're going to have the alkyl chloride product. Finally, let's do this one. We have an alkene, but this time we're doing Br2 and water, so that's halohydrin formation. Recall that the water goes on the more substituted side and the halogen goes on the less substituted side, if you take a look back at that mechanism. And the second step is going to be treating that with NaH. We learned that that's really the only thing that these guys can do, and that's to make the internal epoxide. And so you're going to end up with this. Now we should probably talk about the stereochemistry. Obviously we have a chiral center here, but you're going to end up with a mixture of both possible outcomes. So to make this completely correct, we need to draw those outcomes, and that would be this and this. Now we're looking at what's called a reaction map. And this is to get you guys used to starting to think about how you tie all of these reactions together, because we're going to start needing to think about synthesis problems. So the way these work is that there are missing items. They can be either reagents or products, but everywhere you see a letter, there's something that you need to fill in. And so let's just take a look, for example, at D. We're going from an alkene to an alcohol with a hydroxyl group on the end. So that's an anti-Markovnikov hydration. So what's missing here is going to be BH3, H2O2, OH minus. That's the hydroboration oxidation. Then if we go down this way, we have the hydroxyl group being treated with PBr3. Well, that's just a bromination of an alcohol. So we're here, no stereochemistry. And then finally, that's being treated with sodium cyanide in DMF, which is an SN2 substitution. And so we're going to have this as the product F. Up here, if we look at I, this alkoxide group is going to react with something to give product H. So we don't have enough information there. Let's go a different way and see if we can get some information. We're treating an alcohol with tosyl chloride and pyridine. So that's to make a tosylate. So this is OTS, which is a really nice leaving group. And that leaving group is going to be displaced in an SN2 reaction with methoxide. So what we have here is an ether. I need to count my carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, just to make sure I didn't leave anything off. And so now we have some more information. We know that H is an ether, so that tells us that I needs to be something that can react with an alkoxide to give that ether. That's either going to be a CH3X or a CH3 tosylate. Either one of those would be acceptable answers. Over here, let's kind of tackle this one. If we start back over this way, we're treating the alkene with something to get this functional group. This is the halohydrin. So this looks like this is H2O with Br2. In the next step, this is the epoxide formation, and so this is treating it with NaH, as we saw. And then finally, you're treating an epoxide with acetylide ion, which is C. This is acetylide ion. This is a really strong nucleophile. And what we're doing here is opening the ring. Since these are in strong conditions, we're looking at a ring opening with the less substituted side getting attacked. Let me count my carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Left one off. There we are. And when that opens up, remember you're going to have initially an O minus, so that water is in there just to reprotonate. So this is one possible outcome. The second possible outcome is going to be this one. So that's kind of how these reaction maps work. They take a little getting used to. There are a few in the book, but I recommend that you do as many predict the product questions as you can before you attempt one of these and see how comfortable you are, and then maybe go back and try it again.